Now we are gradually getting into the chapter. We have completed the first law of motion, and remember, go through those examples given in the book. The B part is linear momentum and Newton's second law of motion. This is very important law, and many numericals will be coming, and this is the thing from where the laws of motion starts. And remember, first of all, see this linear momentum. This is a new word to you, so I can take this linear momentum. Exactly, this question might come many times. It was there in ICSE question, in your annual. Remember, we all know what is physical quantity. Any measurable quantity, the quantity which you can measure, is called physical quantity. So for our calculation, for large work, for making large machines, we need few physical quantities according to our requirements, and these are the man-made thing, means we have made this. All physical quantities are made by man. So linear momentum, it is the product of, it is a physical quantity, which is the product of mass and velocity. Remember, velocity. And remember, linear momentum is denoted by P. So P is mass into velocity. So this is very important. You will be requiring this very badly. So what about the SI unit of this one? So linear momentum is the product of mass and velocity. Remember, the SI unit of linear momentum, that is P. Mass is represented by kg and velocity is represented by meter per second. So kg meter per second is the SI unit of momentum. So remember, now I'll start deriving something. Just see here. Let us assume, first of all, a body having mass. This is very important, I am telling you, and see it very carefully. Let a body having mass m moving with initial velocity u. I am repeating myself. A body having mass m moving with initial velocity u. A force F is applied on the body. As a result, the displacement takes place and the velocity of the body becomes v. So what I have told, and this distance you can take it as s. For this time taken, remember, time taken is t. So what I have told? Let a body of mass m, having mass m, moving with initial velocity u. A force F is applied in the direction of the motion of that is, body is moving in one direction and the force is applied in that direction. As a result, what happened? The velocity of the body will increase. So let us assume the final velocity of the body is v. So I can write initial momentum, that is mass into initial velocity. So I can write mu. And what about the final momentum? Final momentum is mass into final velocity. So I can write mv. So what about the change in momentum? So change in momentum. Change means final minus initial. In some cases, initial minus final. So I will be taking final momentum minus initial momentum. Final momentum minus initial momentum. So change in momentum, I can write final momentum is mv and initial momentum is mu. So this is the change in momentum of the body. Therefore, I can write rate of change of momentum. Rate of change of momentum. Momentum. So remember this word rate. When you divide any physical quantity with time, when you divide any physical quantity with time, the thing what you will be obtained is rate. Remember, so rate, this is the change in momentum, mv minus mu. Rate of change of momentum means I will be dividing that above quantity with t divided by t. So easily I can take m common from here, that becomes v minus u divided by t. So rate of change of momentum is equals to m into v minus u by t. Now rate of change of momentum is m into v minus u by t. Now see, v minus u by t, you have learned this from here. We know the first equation of motion comes, that is v equals to u plus at. So this is nothing but acceleration of a body, and we have learned what is acceleration. So I can write rate of change of momentum. Rate of change of momentum is equals to mass into acceleration. So we have done up to this. That is, rate of change of momentum is directly proportional to mass, equals to mass into acceleration. Now I will start second law of motion. Second law of motion, which states that the rate of change of momentum is directly proportional to the force applied. So which state rate of change of momentum is directly proportional to the force applied, and the moment change in momentum takes place in the direction of the applied force. I am not writing the law. Just see here, rate of change of momentum is directly proportional to the force applied. And what force we have applied? We have applied the force F. So from the second law of motion, from second law, we can write force is directly proportional to rate of change of momentum. What is that? Mass into acceleration. So this is a proportionality sign. I have to omit this sign. So I can write F equals, in ratio proportion you have done this, K into M into A, where K is a proportionality constant. Remember this. Proportionality constant, and it is called the force constant. Remember, force constant. Now see, this is the expression. How I'll be coming to the definition of force, just look at here. Now if force applied I am taking is 1, that is, it might be 1 Newton, 1 dyne, whatever. Mass equals to 1, that might be 1 kg, 1 gram, or acceleration is also 1 meter per second square, 1 centimeters per second square. So this equation becomes, see, 1 equals, because force is 1 I have assumed. So K into 1, mass I have assumed 1, and acceleration is 1. That gives me K value is how much? 1. So in physics we can make this constant value 1 very easily according to our wish. So what is the meaning, what is the form of this equation? This equation takes the form of, in place of K, what should I put? 1. So 1 into M into A. Or we can write force equals mass into acceleration. So the question they will be asking you, prove that force equals to mass and mass into acceleration from Newton's second law of motion. We have learned force equal to mass into acceleration, F equals to m into a. Now we will define the force. Definition of force. So very importantly, so now see here I am doing it for SI system. See, what is the value of mass in SI system? 1 kg. And what is the value of acceleration? 1 meter per second square. So the force which acts on a body of mass 1 kg can produce an acceleration of 1 meter per second square. This force is called 1 Newton. Remember. So the force which acts on a body of mass 1 kg produce an acceleration of 1 meter per second square is called 1 Newton. And in CGS system, what is the unit of mass? 1 gram. And what is the unit of acceleration? 1 centimeter per second square. So the force which acts on a body of mass 1 gram can produce an acceleration of 1 centimeter per second square is called 1 dyne. So this is the SI unit of force and this is the CGS unit of force. So very quickly, relation between CGS and SI unit of force. So I can start the derivation like this. 1 Newton is equals 1 kg into 1 meter per second square. Now I'll convert kg into gram. So 1 kg is 1000 gram and 1 meter means 100 centimeter. So see, this is converted gram centimeter per second. So how many zeros are there? 3 plus 2, 5. So 10 to the power 5 gram centimeter per second square. Therefore, very importantly, this is the relation 1 Newton equals 10 to the power 5 dyne. So hope you have understood this one. 1 Newton, so what is 1 Newton? When the force which acts on a body of mass 1 kg produce an acceleration of 1 meter per second square is 1 Newton. And the force which acts on a body of mass 1 gram produce an acceleration of 1 centimeter per second square is known as 1 dyne. What is the relation? 1 Newton equals to 10 to the power 5 dyne.